Hello and welcome to today's webinar presented by Dlubal Software. Today we will be working in our finite element analysis and design software RFEM. The title for today's webinar is Structural Analysis of Glass in RFEM. My name is Amy Heilig. I'll be your presenter today. I'm the CEO and also a technical support and sales engineer in our Philadelphia, Pennsylvania office. My colleague Stefan Frenzel will be today's moderator, answering any questions you might have. He's a product and customer support engineer in our Leipzig, Germany office. If the dialog box seems to get in your way of the presentation when you did log on to this GoToWebinar, you can go ahead and hide that with that orange arrow up at the top. We also want to encourage you to ask questions during the presentation. You can do so in the same dialog box. We'll do our best to get to all the questions, but if by chance we don't, I will certainly send you a follow-up email afterwards. So with that, we can jump right into the webinar. So many of you are familiar with how RFEM and our add-on modules work, but some of you may not be. A quick introduction on this. RFEM is our main program. You can see that over here on the right-hand side. This is where all of the modeling, the loading will be done. We have BIM integration included with Revit, Tekla, AutoCAD. You can go ahead and define your load combinations or have them automatically created according to the ASCE or other international codes. And you can also run a material analysis for things like steel, concrete, timber. RF Glass is our add-on module for glass analysis. And when I say add-on module, it's nothing more than this dialog box that you see over here on the right as well. So a lot of the information from RFEM will be taken from RFEM into this add-on module. Therefore, you won't need to remodel a lot of the things such as geometry. However, with our RF Glass module, there are a few exceptions to that. We will go ahead and define all of the different layers for glass, and what this add-on module will do, we'll go ahead and calculate the equivalent stiffness, import that back into RFEM, rerun the analysis, and then bring those results back into RF Glass. So our materials will be defined in RF Glass for this case. Also, climatic loading will be done in RF Glass. This is very specific to glass, obviously, so there's really no reason to have that in RFEM itself, but other loads such as dead load, live load, and such will be taken from RFEM into RF Glass. And lastly, our analysis and results will all be shown in RF Glass in a table format. We can bounce back to RFEM to view those results graphically as well. So now I want to discuss the different types of glass structures that can be modeled in our program. There are three different types, the first being single layer glass and the most simple type. This option, we can actually use a 2D calculation, which is plate theory, 2D finite elements in order to analyze the single layer glass. We can also run a 3D calculation, which is solid elements, so finite elements in the X, Y, and Z direction. With laminated glass, we have two or more glass panes with a foil or resin layer in between them. And for laminated glass, we have three different options for analysis options. So the first being a 2D calculation with shear coupling. This again will be plate theory. So we have our 2D finite elements and we can consider shear coupling. But keep that in mind, as you can see where this arrow is pointing to this little picture here, that the shear coupling for plate theory is a rigid shear coupling. So you can see that rigid behavior between the different layers of glass and foil. The second option is a 2D calculation without shear coupling. Again, this is plate theory, 2D finite elements. As this picture shows us, we have absolutely no shear coupling behavior between any of the layers. So no relationship there between maybe our first layer, our foil, and our second layer. The third option, being the most accurate option, is a 3D calculation with solid elements. From this picture, you can see that we can accurately get the shear coupling behavior based on the stiffness of all the intermediate layers. Like I said, this is certainly the most accurate option. A downside to this, though, is that your solve time will be longer than typical plate theory. Now, the third option is insulated glass. And insulated glass is shown here by this picture. We have two glass panes on either side. We have a primary seal, we have a secondary seal, and then we have a spacer with our gas in between the two glass panes. This will always use large deformation analysis. With the other two glass types, we can do a linear analysis or a large deformation. Typically with plate theory, you're running a linear analysis. But for insulated glass, we actually only give you the option for 3D calculation with solid elements. That's because when you throw in this gas layer, there's really no other way to get the accurate behavior of the shear coupling between the glass layers with anything other than solids, meaning that plate theory with 2D elements is not applicable for insulated glass. And I want to now discuss the calculation types in RF glass. So over here on the right, this is our add-on module, RF glass, like I said, just a dialog box. And down at the bottom, you will see that we have two different calculation types to choose from, either local or global. And this whole section might seem a little bit confusing now, but I think as we run through our examples today, it will make more sense. So the first being a local calculation. That is where an individual glass surface is analyzed in RF glass. Despite having any supports or boundary members drawn in RFEM, we have to redefine those supports and boundary members in RF glass. And with the local calculation, we can either do a 2D or 3D plate theory or solid analysis. And with insulated glass, this always falls under the local calculation because, like I said, we can only do a 3D analysis type with insulated glass. Now, the other option is a global analysis where the entire model in RFEM is considered. So therefore, things like supports and boundary members that were originally modeled in RFEM will be taken into RF glass. The caveat with this is that we can only do 2D plate theory for this type of analysis. So you can see here from this picture essentially what I'm talking about. A local calculation type, we're only going to be analyzing this one single pane here. And let's say we have these supports shown here in the back. Well, all of these will need to be remodeled in RF glass. As well as these boundary members. Now, if we use the global calculation, we don't have to worry about putting in these boundary supports or any of these boundary members. Everything is taken from RFEM into RF glass. So you're probably wondering, well, why would I ever want to do a local calculation if I have to redefine supports and boundary members? And two reasons for that. One, like I said, we cannot do a 3D solid analysis with a global calculation. So basically, if you have insulated glass or maybe you have very thick glass layers that a plate theory won't give you accurate results, the only option is to run a local calculation. The other reason being that the support types as well as the boundary members can be identified in RF glass in much more detail than what you could ever do in RFEM. So that's kind of the advantage. Again, we'll see that when we go through some examples today of local versus global. So with that, we can jump into RFEM. When you begin a new model, you will see this general data box pop up. We just need to first give it a model name. So I just gave it some arbitrary name. I have the load combination set to ASCE 7. You can see here that we have the Canadian load combinations as well as many international codes as well. And then I have the checkbox to create those combinations automatically. I also always open up my template model. Any model can be saved as a template model, meaning that maybe you have your grid settings the way you'd like, your printout report, your unit set exactly how you want. So then every time you open this template model, everything is ready to go. You don't need to adjust anything next time when you open up a new model. So if I click OK, then this will go ahead and open up a new model for us. And I'm not going to spend too much time today on modeling techniques. We're really just focusing on glass analysis today, but if you are interested more in general modeling in RFEM, we certainly have plenty more webinars such as this that are recorded on our YouTube channel. So how I'm going to begin now is I'm going to draw a line element. You can see here that we have obviously a single line element, but we have many more options such as polylines, ellipses, arcs. So basically any CAD-like feature, you're going to find a lot of those in the program itself. For this option, I'm going to choose an arc by defining first my points at 0 and 0, and then I'm going to use my snap point to 6 feet. And then you can see now I want to define my radius. I want to actually reverse the orientation and define my radius at 6 feet. So now I just have a simple line element. This isn't a member, it's just a line. And then I can actually select this line, right-click, and I can extrude the line into a surface. Now, if you were present in my last webinar on cross-laminated timber, the glass module somewhat acts the same way. And how I mean that is the program is asking us now, what material do we want to use when extruding this line into a surface? And realistically, this doesn't matter right now for glass. This concrete is just a placeholder. So it doesn't matter if I choose concrete, I choose steel, I choose aluminum. It's just simply a placeholder. The height, though, we do want to specify the correct geometry in the program, with the exception of the thickness. Thickness doesn't matter either because all of our layers and such we will be defining in RF glass. So if I hit apply, then I can see that I have this surface now created with just a few clicks of a button. The next thing to consider is maybe we have some type of handrail on our glass panel here, and I don't want to model the handrail itself, but I'd like to create a line so that I can add in a line load to this surface. So all I'm going to do is I'm going to select this bottom line here and use my move and copy tool and move it up 3 feet in the positive Z direction. Now you can see that that line is integrated in that surface. So quickly adding some load cases. Here I will go ahead and add my first load case, dead load, and you can see that the self weight is automatically checked on for self weight. I'm going to create a new load case called wind load pressure. And you always want to define the correct action category. And the reason why is the program automatically created all of these ASCE load combinations. If you don't apply the correct action category, then you're going to get the wrong load factors. So I'm going to make a quick copy of wind load pressure, but call this one suction, and then make one more load case of live load and give it the live action category. Okay, so I can click OK here. Now, if I go to my drop-down box, you'll see that the program automatically created all of those ASCE load combinations. I'm going to skip dead load for now. We'll just consider self-weight, but wind load pressure, we want to add our first surface load on. If I right-click, I can turn on my local axis system, and I want to add a new surface load. Because we have a curved surface, I want to apply this wind load pressure on my surface in the local Z direction. And you'll notice down here the little picture updates depending on what direction you're applying your load to, which is nice. So in this case, I want the local Z direction. I want my magnitude to be negative 0.03 KSF. And all I need to do is click on the surface and my area load is applied. I'm going to switch load cases to section. I'm going to again add a new load in the local Z direction, but this time it will be 0.02 KSF on the other side. And then lastly, we have live load where I will add in a new line load. This I'm going to apply in the global Y direction with a magnitude of 0.07. And then all I need to do is to click on that line. So now we have all of our loads added to this surface. All of our load combinations are done. I want to check my finite element mesh settings. So if I go to calculate and FE mesh settings, the default is set at 1 foot. The length of 1 foot would probably be okay in this situation since we really don't have much going on in this surface, but it is only 6 by 9 feet. So maybe we want to decrease this to something more like 0.5 feet. If I go to calculate, generate FE mesh, now we can see the FE mesh is automatically generated. Keep in mind this is different than some of the other programs in that all finite element meshing is done automatically. If I were to move this line up an inch, everything would automatically be readjusted. So you never have to worry about changes happening in your model and the finite element having to readjust that manually. Everything is done automatically. Now we are ready to jump into our add-on module. So we have this extremely long list of add-on modules, but if I right-click on any of the add-on modules, I can select it at my favorite, which will automatically move it up to the top of the list. So now I can launch RF Glass. Okay, so taking a look at RF Glass, as I mentioned, this is the add-on module, nothing more than a dialog box. You can see here that all of our load combinations were brought over from RFEM. The first question it's asking us is what surface do we want to go ahead and design? And you can check the all checkbox since we only have one surface. Now the other couple things to note here is that we do have the German annex for the standard to go ahead and do glass design. For us, we're going to be doing just an analysis, so we will be choosing no standard. And there's a little bit of a translation issue right now, but don't worry, that will be fixed soon. This is none in German. And the ultimate limit state, we need to select which load cases we want to consider. So I'm just going to select all of my LRFD load cases. Now under serviceability, I'll simply select all of my ASD load combinations. And remember back to the PowerPoint, this is what we were discussing on local versus global. My two examples now will be local. So the first one will be local, individual glass surface. We'll focus on that and then we'll get into global a little bit later. And with any add-on module, you just simply work down the list. And extremely intuitive to use. The program kind of sets up your workflow for you. So we're moving on to layers here. It's asking us, okay, so we can create a new composition. You can rename this. You can create as many compositions as you'd like for different surfaces in your model. For us, we'll obviously only have one composition for our one surface. We need to select which surface this applies to, and we can define our first layer type. So our first layer type will be glass, and here will be the option to jump into our material libraries database. And typically the standard when you select this will be under the material category glass, and all of these options will be listed. We don't quite yet have the ASTM materials in there, but really that's no problem at all. I added this thermally toughened float glass to my ASTM standard. So anytime that you add in a new material, this will of course be remembered for any future files or models that you were to create with this glass module. All of our properties are shown in the same dialog box, so everything is okay there. Now my thickness, I want it to be 0.2 inches. Again, all of our material properties are shown to the right here. Our next layer will be foil. And with this, believe it or not, we actually do have a lot of ASTM foil materials already integrated in the program. For this particular case, I will use 20 degrees Celsius at 1 minute. Again, the foil material properties are shown here. The thickness of 0.01 inches is fine. And lastly, I choose my last glass layer. The program's smart enough to know that, okay, I used ASTM for my last glass layer. I'll also use the same thickness, so that's nice that we don't need to go back into the material library. We don't even need to define a different thickness if we don't want to. One thing to note here, you can export or import directly from Excel. So if you have some crazy complicated glass layering going on and you have all the properties defined in the same format in Excel, well, at the click of a button, you can go ahead and import it in directly into the program. So I'm going to edit my composition details, and this brings up a lot of what we were discussing in the PowerPoint. So you can see here with my method of analysis, I have either a linear analysis or a large deformation analysis to choose from. For right now, I'll just go ahead and stick with the linear analysis. Now, the modeling of the laminated glass, I have either 2D or 3D, so we understand plate theory versus solids, but this third option is something we didn't discuss. The program can automatically turn a 2D model into a 3D solid element model if the ratio of the shear modulus times the thickness of the glass over the shear modulus times the thickness of the foil is greater than some ratio. The default ratio is 1,000, but you can change this to whatever you'd like. So if your depth of your glass layers is getting a little bit too thick for a plate analysis, well, the program can automatically turn that into a solid model. For us, we'll just stick with 2D to keep it simple for this first example. Now, calculation options, save created temporary models. What is this? And with our RF glass module, which is a little bit different than a lot of our other modules, the program is actually creating a whole nother model behind the scenes. So by checking this checkbox, we can actually open up that model just like we would any other RFEM file to view how the program put all these layers together to create our glass surface. In our next example, I'll show you this, so it's nothing to worry about right now at the moment. Consider coupling. Remember, with plate theory, we either have rigid coupling or no coupling at all. If I uncheck coupling, I no longer have the option to turn it to a solid analysis. Activate FE mesh refinement. This is if you wanted to change your FE mesh of this surface only, or any of the surfaces that you define for this composition. This is nice because I don't have to go back into RFEM, redo my finite element if all I want to change is just simply the surface in here. So that's certainly an option as well. Okay, so also notice that we get this nice picture here of the different glass layers. Depending on which line I'm clicking on here, this arrow will be synced with whichever layer is shown in this little diagram. Something important to note here, the local axis Z is the positive direction is facing towards the bottom of the glass. So this is the bottom of the glass, and know that the positive Z axis of our surface is also pointing towards the bottom of the glass. So for this example, it doesn't really matter because we have symmetry between the top and bottom layers, but our next example will be different than that because we won't have symmetry. So you want to make sure that the local Z-axis and the bottom of your glass are correct, that they are aligned correct. All right, moving on down our list, line supports. In RFEM, I didn't define any line support. So if I were to try and run that model right now, I'd obviously get an instability because I have nothing supporting that surface. So this is where I was telling you in RF glass, we can go ahead and define these line supports. The first thing that I need to do, and you'll notice here I have my picture, I can rotate it, I can scroll in, is to choose my first lines. So if I choose them graphically and just using my AutoCAD type features of just dragging a selection box, I chose the left and top lines here. And if I click on support type, you will see all of these different hinged options. As I go ahead and scroll through these, you'll notice that the support types are changing down here. If this still doesn't make a whole lot of sense to you, you can always click on this help manual here. And what this does is it will bring up our manual for RF glass. And if you scroll down just a little bit, here are all these different hinge types. And it's nice because it's set up in a way, okay, well, if you're doing plate theory under the 2D calculation, this is how the hinge type will look. Now, if we're doing a solid model, this is how the hinge type would look for these different, hinge type 1, hinge type 2. So this is what I was saying, that the benefit of using a local analysis in RF glass is that you can get very detailed in how your glass layers are supported. In RFEM, you don't have these options. You can do it, it's just much more complicated. So in RF glass, it allows you to get a little bit more detailed. So for us, we will choose hinge type 3. Then I want to choose my other 2 lines here. And I can always select a user defined as well. I don't have to use these already determined hinge types in here, and maybe I want to unselect translation in the X direction. Keep in mind you can always select springs as well, so you don't necessarily just have to have a free or fixed situation. Moving on down the line to nodal supports, exact same concept. Just if you were to have nodal supports instead of line supports, this is where you would go ahead and define it. Boundary members. So it's not uncommon to maybe have something like a channel member up at the top here of our glass surface. Well, I didn't model that in RFEM, and because I'm using the local glass analysis type, I want to define that boundary member here. So the first thing I need to do is I need to select where I want that member to run. And you'll notice that everything is just set to center line because I'm using 2D plate analysis. I don't have any cross sections defined in RFEM. And normally you would think, okay, I probably need to go back into RFEM, create some cross sections, but the nice thing is I can do everything from this add-on module. So up pops my cross section library. For this case, maybe I'll choose a type of channel here just for geometry purposes, and here are all my AISC shapes. Maybe I want a 3x5. Concrete is obviously not the right material for this, so we can easily edit this as well and jump into our material database. Maybe we want something more like aluminum from the ADM. Well, I already have aluminum set in one of my favorites group for USA as 6063 T6. Here are all of my properties for that particular material. I can click OK in all of these, and if I zoom in, I have a nice rendered shape of my channel. You can also rotate it if you need, and the program will automatically update that as well. So for analysis purposes, we certainly want to take into account the stiffness from this member here. So that's the whole purpose of defining boundary members. Maybe you have a boundary member with nodal supports on either side instead of a line support. That can all be modeled in here as well. So this is just for example purposes. I will delete this for now. And lastly, we will jump into the serviceability data. So this is nice in the sense that if I go to my standard button down here, I have my serviceability limiting deflection ratios. I have 3 different types of combinations, characteristic, frequent, and quasi-permanent, and you can see that I can change these ratios for these 3 different combination types to whatever I'd like. Default is L over 100, and for cantilevers it's L over 50. If I go back to my very first tab under serviceability, here's where those 3 different combination types fall into place. So if you want different limiting deflection ratios for these different serviceability load combinations, it's possible to do it in one analysis without having to rerun several times with different deflection ratios. The only thing I need to define is my surface. Now the reference length, do I want to use the minimum border line, the maximum border line, or do I want to define my own? In our case, a conservative option would be the minimum border line at 6.28 feet, and if it was a cantilever, I could check this option here. Last thing to check is the details button. You can see that we have all of these options for what stresses we want to show in the final analysis. So I can easily uncheck any of these if I don't want to see them. I could check them if I do. And under the results, there's a few other options for what you want to see in your calculations. For example, maybe we want to see line support reactions. And with that, we are ready to solve. So what the program's doing now is it's taking each stiffness layer from the glass, creating a more global stiffness, exporting it back into RFEM, rerunning the analysis, now bringing all of the results back into RF glass. And now we have this results menu available. here we can view our max stresses and our ratios by either the loading. So we have our different load combinations, load combination number 1, number 2, number 3, and remember this is ultimate limit design. We also have our max stress ratio by the surface. We only have one surface defined, so of course we only have surface number 2 shown here. And then we have our max stress ratio by the composition. We only have one composition defined. And with this, we will get our different stresses for the different layers, layer number 1 and number 3. We have our existing stresses due to the actual load combination, and then we have our limiting stresses. And of course, we get a ratio. The max ratio is shown down here. We have a nice green smiley face because he's well under 1.0. The other thing to note is that you can export this directly into Excel. So Excel obviously has a lot more capabilities in terms of sorting data and such. So this is a nice feature to have, that if you want to have a little bit more control over that, then just click the button. It automatically opens up Excel and brings all of your data in there automatically. You'll see here that we have our stress diagram shown. We have a rigid coupling, so viewing the stress diagram, this makes sense for what we're seeing. We have obviously a relationship between our top layer and our bottom layer with our stresses, and in between is the foil layer. We can see our line support reactions in a table format, as well as the max displacements. Remember, these max displacements are based on the ratios L over 100 that we gave it, and then we get our ratio of our limiting deflection as 0.01, well under 1.0, so we're perfectly fine there. And lastly, we get a parts list or material takeoff for the surfaces that we defined in this add-on module. Jumping back to the max stress ratios by either loading, surface, composition, there's another option down here called graphics. And with graphics, this will immediately bring us back into RFEM. And here we can view the different stresses by contour lines. So you'll notice that the results option popped up here in our project navigator. If I look up here, it shows me that I'm still under RF glass. Even my drop down here shows me I'm under the results of RF glass, and here I can easily jump right back into that add-on module. So it's nice here if you want to visually see what's going on with these different stresses. Okay, so that concludes the first example. Now, for the second example, I'm going to use this same surface, but I'm going to turn this into an insulated glass example. Time savings, the geometry is already created, the loading's already created, and we're just going to see a lot of the similarities and differences between a 2D plate theory versus like an insulated glass solid model. I'm back in my data tab under my project navigator, and what I can do is to actually just right click here on RF glass and delete all of my data. It's asking me, do I really want to delete this? Yes, I do, and we are back to square one with just a simple concrete surface is what it's shown now. So here I will launch my RF glass again, and we don't need to spend much time on some of this. One thing I do want to do real quick that I forgot, let's go back into our load cases, and I want to create one more load case here called climatic load. This is for my gas pressures of my insulating glass that I'm about to create. I'm going to create a new load case here called self-straining force. You certainly can put your climatic loads into any one of these load cases that you want, but keep in mind, maybe climatic loads you want a load factor of 1.0. When you put it in with dead load, well, now it has the same load factors as dead load. So most likely you're going to want to keep them separate from these other action categories, which is why I created climatic load. This does have a load factor in our ASCE load combinations of 1.0. So I can launch RF glass again. Now you can see that my load cases are a little bit longer. I now have this T for temperature included in here as well. So for ultimate limit state design, I'm choosing all of my LRFD equations, and serviceability, I will choose all of my ASD load combinations. We are still going to stick with the German none here for our standard, and the calculation type will be local. Again, this is another local design, but you'll see here under layers that we want to first choose our surface. Nothing new here. Now our first layer type will be glass. The program remembers the ASTM. This time I want a thickness of 0.06 and, or sorry, 0.6, and then I want to create my next layer of gas. The minute I put in a gas layer, the add-on module says, okay, this has to be a solid analysis. I can no longer do plate theory. That's just a limiting effect. When you choose gas, there's no way to do a plate analysis. For my materials library, for my gases, these are the options that are already in the program, default in the program. Argon is a pretty common one for insulating glass. Here are our properties, again shown here. Maybe I want my thickness to be 0.65. I'm going to choose another glass layer of 0.50. And then a foil layer, we'll keep it at 0.01, that's fine. And lastly, one more glass layer at 0.5. Now let's take a look at our details of this composition now. You'll notice some changes in comparison to what we were viewing last time. Linear analysis, no longer an option. We only can do large deformation analysis. As I mentioned, Newton-Raphson is the type of large deformation analysis we will do. You do have the option here to choose with a constant stiffness matrix. So this will obviously speed up your calculation time a little bit, but maybe not as accurate of results because you're not getting that nonlinear behavior with the different stiffness matrix for each iteration. It's up to you though on which option you'd like to choose. Number of load increments. This runs parallel with our finite element mesh. Anybody who's done finite element modeling knows that if you have an extremely large mesh, you can get very inaccurate results. However, if you continue to submesh your elements to something very small, well, your solve time also increases, and at some point, your results aren't going to change very much. It's the exact same thing with load increments. Maybe one load increment won't give you the correct results, but maybe 10 load increments is too many. It slows down your solve time, and your results aren't any different than what 5 load increments would have been. Default is 5 here, but you can certainly feel free to change this if you'd like. Modeling of laminated glass, we only have one option because we have insulated glass. And then the calculation options, this is where I want to show you guys save created temporary models. I think it's a very cool thing that this add-on module does in the background, so we can actually view the glass panel after we're done here solving. If I uncheck consider coupling, everything turns to plate theory again, which is just not relevant for this case. We will always consider coupling for a solid model. Okay, remember what I said with the local z-axis direction pointing towards the bottom. Most likely this is going to be the external part of our surface, our glass layers. And if I were to double check this, everything looks okay that the local z-axis is the bottom here. Moving on down the line supports, nothing new here for the most part, so I'll quickly run through this. There is one thing that I do want to show you. If I choose hinge type 3, just like we did last time, you'll notice now that I have 3 different layers, whereas before I only had one option. So with solid elements, if I actually zoom in here, you can see now that I have these different solid elements where I can apply these nodal supports at the different layers. As I scroll through here in the table, the little picture updates on which layer I'm at. So that's nice that everything is synced here so that I can see how exactly I'm applying these line supports. Sorry, these are line supports that we're in. Same thing with the bottom line and the right line. Maybe we want to choose user defined here. I'm going to release translation, but now I need to do it for all 3 layers. Nodal supports, same setup. If we were to have nodal supports, we will skip this for now. Boundary members, same concept as well. The one thing that I did want to show you though, if I do choose the top line again for let's say that channel, now I get to choose which layer I want to place that channel on. Again, scrolling down in here, if I choose layer 1, the picture down here will jump to that layer. I can also then choose upper edge, center line, or the lower edge within each layer of where exactly I want to place that boundary member. So this is what I was saying, that RF glass allows you to really get detailed, especially with this solid model, and how exactly these supports as well as boundary members are framing into your glass panel. Again, RFEM would not allow you to do this very easily. This is just for demonstration purposes once again, so we will delete this row. Climatic load parameters. So this is something new that popped up when we did define a gas layer. We probably need to take into account some climatic loads. Now, there is this checkbox here, automatic gas temperature calculation. If I check this, you'll see we get some very complex variables here. Realistically, unless you're a glass expert and you really know what you're doing here, you probably will never have this checked on. This is all kind of behind the scenes, but it does give you control over some of the variables and such if you want to. I do have a document write-up. If anybody wants to see this, feel free to email me and I can give you more information on this, but I'm not going to cover it now. So with this unchecked, I think that these are pretty straightforward, which is nice. The first thing that it's asking us, okay, well, where is this glass panel manufactured? The atmospheric pressure is default 14.9, that's fine. Let's say this glass panel was created at sea level. So we will automatically put in our altitude of 0 here. The temperature, let's say it's something more like 65 degrees. Now, mounting is the next option here. Where will this glass panel end up? Atmospheric pressure, it's set at 14.6, that's fine. Maybe the altitude is 2,000 feet, so the altitude difference is calculated. The air temperature, because this is summer, let's say it gets pretty hot at 90 degrees. The gas temperature can get up to 102, that's fine. Internal air temperature, let's say it gets up to 70 degrees. So with these settings, the program will automatically calculate those gas pressures for you, those loads. But what we do need to define is a load case for these climatic loads. That's why I created this climatic load case. Like I said, you can choose any one of these, dead load, wind load, live load, but you probably don't want to because it's not going to have the same load factor that you'd want for your climatic loads. Climatic load winter tab up here. Everything's exactly the same. The only thing that we need to do now is just to define our different temperatures for winter. So maybe the temperature in winter at sea level is 65 degrees year-round. Mounting, however, where this will end up, the altitude will be 2,000 feet. The external air temperature can get down to 20 degrees. The gas temperature, 35 degrees is fine. The internal air temperature, let's say, can get down to 62 degrees. Now, again, for winter, we need to go ahead and set our load cases. The program obviously knows that we'll never have summer and winter loads together. So it will actually create separate load combinations for summer versus winter. So that's something that you don't have to take into account. The program's smart enough to know that. Moving on down the list, insulating glass unit. So here is where we can consider our secondary seal options. For this, I want to jump back into the PowerPoint quickly because this is actually a little bit more complicated than what you would initially think. For a secondary seal, now there is the option, this is exactly what we were just doing, what you just saw in the RF glass module. So if I had this option unchecked, there is the use helper supports on gas layers. That's now grayed out in the program. So what exactly are these helper supports, since there's not much information in the add-on module itself? Well, when I have the secondary seal unchecked, meaning there's nothing there, these helper supports will be applied in our glass surface. Taking a look at this picture down here, glass panels are pretty stiff, maybe around 10,000 KSI. However, RFEM will model a soft material at either end, something closer to 1.5 KSI. Now, when we don't have these helper supports applied, we get some sort of deflection that maybe looks like this. This is obviously not desired behavior. This is from the gas pressures, and then we're getting our deflection at our sides. Now, when we add in these helper supports, we add stiffness to the ends here, and we'll get more of a desired deflection with our glass panes. So that is the whole purpose of these helper supports. Now, remember, when you have the secondary seal unchecked, we automatically apply that in for you. If you were to check the secondary seal, you now have the option to uncheck or check this helper supports. And the reason why is because now you have control over modeling the exact stiffness at these ends. So if you don't want to consider helper supports, which are very rigid, then you just want to make sure to correctly model your secondary seal, but also include the stiffness of your spacer here with all of the correct properties. And then you should get the desired correct behavior considering the stiffness of this secondary seal. If you're unsure, then you can always leave this helper supports checked as well. So that's just a little bit more on what this option is. For us, we will leave this unchecked for now, therefore the helper supports will be used in the background. The number of finite element layers in gas layers. So our gas layer is only 0.65 inches deep. 2 layers is probably fine for that. If you had something larger, you can always increase the number of layers. This is something that I think is pretty cool for this add-on module. Force load distribution. You can see my 5 load cases here, and we give you the option to determine what percentage is applied to the external glass versus the internal glass. So dead load, we only have self-weight. Maybe we want to apply 50 and 50 to the external and internal. Wind load pressure, we want 100% to be on the external side of this glass. Wind load suction, we want 100% to be on the internal. Live load, it's a handrail, so maybe we want 100% on the internal. Climatic loading, maybe we want 50 and 50. So a little bit more control on where exactly these loads are being applied to your glass surface. And lastly, we have our serviceability data. Here we can just select the surface. It's applying it back to those those service load combinations and the ratios that we've set here. And with that said, we are now ready to run an analysis. As I mentioned before, a solid analysis takes much longer than typical plate theory. So I already went ahead and ran this result because we don't want to be sitting around for a few minutes or so with nothing to talk about. So here are the results for this exact same model that we were running. Let me open back up my RF glass module, and then this is what it should look like once we are done with the analysis. Nothing really too different from our plate. Obviously, we're going to have more layers here for our stresses. You can see my max ratio is 0.99. Maybe for design, this is a little bit high. We wanted something more like 0.9. Regardless, we still get our green smiley face because we are under 1.0. Again, feel free to export any of this data into Excel. Pretty much the same thing that you would see before. The one thing I did want to show you guys is under, let's go to gas pressure, for example. You can see here the loading CO2 summer, CO2 winter. So like I said, the program creates 2 load combinations, one for summer and one for winter. And here you can see all of your different gas pressures. Jumping back to one of these stresses here, we can see our stress diagram. And now we have our glass layer. Gas, we obviously won't have any stresses, and then we have our other 2 glass layers. So with this, we get the accurate shear coupling behavior based on the stiffnesses of our intermediate layers, which you can see here is modeled quite nicely with these diagrams that you can see for each layer. Jumping to our graphics, again, we have control over what stresses maybe we want to see graphically based on the contours. So nothing too different, essentially, than what we saw for the results from our plate theory. Now, remember how I checked on that checkbox to save that model in the background that it's creating? Well, if I go ahead and show you guys my desktop, here is the model insulated glass results. I just saved it to a folder on my desktop, and automatically the program created these 3 models as well. So I had nothing to do with creating these. These were the ones that were created behind the scenes, and the program saves it because I checked that checkbox. You can see here we have W for winter, we have S for summer, and then we have a third option which doesn't include climatic loading. So if I were to open up one of these options, let's say the winter one, which I already have pulled up here in my program, this is what I was talking about when I said it creates this model in the background. I can zoom in here and I can see my solid elements. I have my first solid for my glass layer. There's 2 layers here. If I zoom in really close, here's my foil layer. Here's my other glass layer. Here's my bigger gas layer, and then I have my other glass layer. I can turn this into wireframe too to kind of see what's going on. Now, the other thing to notice as well are the supports at all the different layers. So this was everything that we defined in RF glass. And like I said, you could sit here and model this in RFEM, but it's going to take you a while. Whereas RF glass, you just give it some of the properties and the program creates everything automatically. That would even include our climatic loading. If I show you guys now our new LC5 for climatic loading, we now have these surface pressures on our glass unit. So this is what's going on behind the scenes, is that the program is automatically creating this solid model for us. So I wanted to show you guys what exactly that checkbox does when we want to save and see these models. Okay, so that concludes the local calculation types. So probably everyone wants to know, well, what about the global? Maybe some people are a little bit more interested in that. Well, let's take a look at this example here. So this was modeled by one of our glass engineers, and I'm going to quickly turn off the FE mesh and our FE mesh refinements. You'll notice here people ask often, well, can you put holes in your glass? Yes. That's no problem at all. You can see here that this is a glass surface and we modeled a hole in it right here. Now what we also did was we went ahead and modeled a contact element, a contact surface. So this top one, if we click on it, is a rigid surface. If I click on this middle contact surface here, sorry, let me zoom out. If we go into an elevation view, what exactly this is really an exact model of how this support will act with this glass panel. If I double click here, I have a contact surface. I look at my nonlinear settings here, I have failure under tension. So basically this support will fail, this contact support will fail if any tension is experienced. And again, on the bottom we have another rigid surface. So this is just a more detailed modeling of the glass and its supports. This is something that you obviously can't define in RF glass. This was modeled in RFEM, our main program. So when we, and let me show you guys too the finite element mesh. Let me turn that back on. This is pretty powerful as well. So the finite element mesh you can see here is set at some arbitrary number. But the other thing that we did is we went ahead and added some finite element mesh refinements here, and that's what these circles are about. So if I double click on one to take a look at it, we made a finite element mesh around a node. We set the inner length to something very small. Full precision will show it's at 0.0003, and then the outer is 0.02 feet. So the program will gradually increase so that we have this smaller finite element mesh at the node here, which is kind of required because we're getting some small elements here. Jumping into our RF glass module, so you'll notice under the general data, and I already ran the results for this, but I now have global selected. And if I have global selected, take a look at the input data. I have a lot less options here. I don't have the options for nodal supports, for line supports, for boundary members. I have no climatic loading because I can't analyze any type of insulated glass here. With global, remember that we can only do a plate analysis. So basically what the program's doing is it's taking all of our supports, all of the boundary elements, it's taking it from RFEM into this. The only reason now that we're really using RF glass is to get the correct stiffness for our different glass layers. With this case, we only have one glass layer, thermally toughened float glass. So nothing too complicated here. We still can set our serviceability data according to those ratios. And then we can run our analysis. We still get our results here for our glass layer. Again, we only have one layer, so that's why our stress diagram looks as such with one layer. And basically, we have the same output type as what we saw before. But keep in mind that this is a 2D analysis. If I do go back to layers, I wanted to quickly show you this. Notice that all of the 2D, 3D, nonlinear analysis, that's all gone now with global. You no longer have any of those options. This is a 2D analysis, linear analysis. Okay, so I can also jump back into my graphics, and we have these nice contours now of our different stresses. Maybe one thing we want to do is to make a section cut through one of these. Oops, let me go back to graphics here. Okay, so we can create a section cut. I don't know why it's not letting me do that. Oh, probably because I need to go to the results. Sorry about that. Okay, so choosing one of these section cuts, maybe I want a little bit more detail through these supports here because the contours are nice, but we don't really get any numerical results. Well, here we can go ahead and turn on, let's say, one of our normal forces, sigma 1, and then you can turn on any of the stresses that you like, but here you can view it across that surface where we just made our cut for numbers instead of just purely contours. And the last example that I want to show you guys, which is probably something, you know, you have maybe a full building modeled and you just have a glass balcony or a glass partition that you want to analyze with the rest of this building. So rather than this single glass panel here, maybe you want something more such as this. So this was modeled by one of our other engineers. It's basically a glass type balcony. You can see here if I zoom in, I have my different glass surfaces. There's a little gap model between them. We even modeled the handrail attaching to the glass surfaces by a single node. Then we also have these nodal supports at 4 different points. I can decrease the size of this so that we can see it a little bit better. I have these nodal supports at 4 different points along the glass. We modeled in a little member to take into account eccentricity. So this might be something more of an application where you have a bigger structure. You don't want to sit there and just model one glass element at a time. Keep in mind, though, you can always do a local calculation within a larger model. That's certainly possible. You don't have to have just a single surface in one RFEM model. So I could do a local calculation on just this single surface here. So for this case, though, maybe we want to do more of a global analysis. I launched my RF glass add-on module. You'll notice here I have global selected for the whole model in RFEM. Again, similar to what we saw before, this time I didn't consider coupling, so we'll see how the stress diagram is influenced by that. So we have no coupling behavior between the different glass layers. Again, we have no option for 3D solids for nonlinear analysis because we are now in global. Here, though, are our different glass layers for laminated glass, serviceability data, everything's the same here. Now, taking a look at our results with a max stress ratio by loading, surface, or composition, here's where that no coupling behavior comes into play. Normally, we'd see a stress diagram similar to this top layer throughout the entire depth if we had rigid coupling considered. But we have 0 coupling considered, so we have no interaction between the top and bottom layers. So that's why our stress diagrams are completely separate here. Again, I can view everything graphically for my different stresses, which is nice now because this is beneficial. You know, if I were to do a local analysis of one glass surface, I would need to take into account maybe the stiffness of this handrail coming in as a nodal support, so it gets a little bit more complicated. And then maybe I need to set these nodal supports as with this eccentricity taken into account. So there's certainly some benefit to a global analysis, but again, if you have very thick layers of glass, that a solid element would give you better results, or you have insulated glass, which in this case you obviously wouldn't have insulated glass, but just keep that in mind that global is not an option. But for a situation like this, maybe this is perfectly fine to consider plate theory, and then we get our results for the entire structure. Then the other advantage to this is tying it into other members in the model. So for example, let's say that we wanted to model or to take a look at the results of our steel handrail. So we have another add-on module called RF Steel that will basically just give you a stress analysis of a steel section, just comparing the demand stresses to the limiting stresses. And with that, now we can view the results graphically of, you know, any of the stresses and stress ratios for this handrail. So that's what's nice about tying this in, of course, to the rest of the model with a global analysis. And that sums up the global options here. One quick thing that I did want to show you guys, which I think is pretty powerful, if we let's say we jump back to our results here for our RF glass. Let's say we wanted to print off all of these different pictures here for our contours of our stresses. Well, normally in a lot of other programs, you would need to take a picture, put it in your printout report, come back, change a view, take another picture, put it in the printout report. For us, we have this option called mass print. For this, you'll see the option mass print here. If I go into the details of this under my results, I see all of the results that I'm viewing over here, and now I can select all of these stresses, including my ratios. If I click OK, maybe I need to set the size of my picture. I can set it at 50% of the page, that's fine. I click OK, and what the program's doing is it's automatically creating all of these pictures for us and putting it directly into the printout report. I think our printout report is one of the strongest features, especially in comparison to a lot of other programs that you're used to. It's laid out very nicely, and you can see here that the pictures were automatically put in based on all of those different stresses. So I can jump through them over here in the table of contents or just view them graphically, and everything was automatically put in there. Let's say maybe for this one, I don't really like that view. I can click on edit, change the view to maybe a front view here. I click back, and the printout report will automatically be updated with that new view, as you can see here. The other important thing to note, if anything were to change with your model, let's say a loading or you rerun an analysis, these pictures all update automatically too. So you don't have to worry about going back, reprinting them again if any slight change was made. So something that's really nice about our printout report. Okay, so going back to the PowerPoint, we can sum up today's webinar. You can visit our website at dlubal.com. We have plenty more information on the RF glass module as well as RFEM and any other add-on modules you might be interested in. We have plenty of social media sites, including the YouTube site that I mentioned before, a lot of other webinars such as this one that have been recorded that were posted on our YouTube site, which you can just search by keyword. The email for our Philadelphia office is info-us@dlubal.com. Our phone number here is 267-702-2815. We will have more upcoming webinars, usually about once a month. You can register on our website at dlubal.com under Support and Learning and Webinars. Many of you are also familiar that I try and send out just a couple reminder emails before these webinars occur as well. So you can sign up through the emails as well. If you do want PDH credit for today, I'd be more than happy to issue a certificate of completion. Just email me at info-us@dlubal.com and I can go ahead and get that over to you. With that said, that concludes today's webinar. I want to thank everyone for attending today, and I hope to see you at the next one. Thank you.